In 1998, two teams of astronomers made a discovery that shouldn't have been possible. They were measuring the brightness of distant supernovae, cosmic explosions so powerful they briefly outshine entire galaxies, trying to determine how fast the universe's expansion was slowing down due to gravity. Instead, they found that the expansion wasn't slowing at all. It was accelerating. The universe is being torn apart by an invisible force that comprises 68% of all existence, yet remains completely unexplained by physics. We call it dark energy, but that name is just a placeholder for our profound ignorance. We have no idea what it is, where it comes from, or why it exists. And here's what keeps cosmologists awake at night. Recent measurements suggest dark energy isn't constant. It's changing, growing stronger. The acceleration is accelerating. If this trend continues, if dark energy keeps intensifying at its current rate, then within a finite and calculable time frame, the force tearing space-time apart will become so powerful that atoms themselves will be ripped to shreds. Molecules will disintegrate, planets will explode, stars will be shredded. Eventually, even the quantum fields that define reality will be torn apart. This is called the Big Rip, and the most recent observations suggest it might happen in as little as 22 billion years. Today, we journey through evidence that challenges our most fundamental assumptions about time, eternity, and the fate of everything that exists. We'll explore why some physicists now believe the universe has an expiration date, and why that date might be sooner than anyone imagined. Pause. The clock is ticking. Let's begin. Act 1. The Discovery. 2 minutes. January 1998. The High-Z Supernova Search Team, led by Adam Rees at the Space Telescope Science Institute, published data that would earn them the Nobel Prize and simultaneously terrify the physics community. They had been observing Type 1a supernovae, a specific kind of stellar explosion that serves as a standard candle in astronomy. These explosions always reach approximately the same peak brightness, which means by measuring how bright they appear from Earth, we can calculate exactly how far away they are. The team expected to measure how much the universe's expansion had decelerated over cosmic history. Every object in the universe has mass, and mass creates gravity, so gravity should be pulling everything back together, slowing the expansion that began with the Big Bang. What they found was the opposite. Distant supernovae, those whose light had traveled for billions of years to reach us, appeared dimmer than they should be, not because something was obscuring them, but because they were farther away than expected. The only explanation, the universe's expansion had accelerated during the time the light was traveling toward us. Like throwing a ball up in the air and watching it accelerate upward instead of falling back down, Rees later explained. Everything we understood about gravity said this shouldn't be possible. The Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, independently confirmed the finding using a different sample of supernovae. Both teams arrived at the same shocking conclusion. Approximately 6 billion years ago, the universe's expansion began accelerating. Something was pushing space-time apart with increasing force. To explain this acceleration, physicists invoked Einstein's cosmological constant, a term he had introduced into general relativity in 1917 to allow for a static universe, then abandoned when Hubble discovered cosmic expansion. The cosmological constant represented a property of space itself. empty vacuum possesses energy that creates a repulsive gravitational effect. Einstein had called it his greatest blunder. Now it appeared he had been right after all, though not in the way he'd intended. The discovery revolutionized cosmology, but it also introduced a profound mystery. If the accelerating expansion was caused by vacuum energy, energy inherent to empty space, then that energy should be constant. The energy density of empty space shouldn't change over time. But constant dark energy leads to a specific prediction about the universe's fate: eternal expansion. Galaxies would drift apart forever, eventually moving so far away that their light could never reach each other. The universe would end not in a dramatic collapse or explosion, but in cold, dark isolation, what cosmologists call heat death. Depressing, certainly, but predictable, comprehensible, safe. The alternative was far more disturbing. In 2003, Robert Caldwell, a physicist at Dartmouth College, published a paper exploring what would happen if dark energy wasn't actually constant. What if it was dynamical, changing over time, growing stronger or weaker? If dark energy was weakening, the universe's expansion would eventually decelerate and possibly reverse, leading to a big crunch, everything collapsing back to a singularity. Dramatic, but at least everything would be over quickly. But if dark energy was strengthening, Caldwell worked through the mathematics carefully. He found that if dark energy density increased over time, the acceleration of expansion would keep increasing too, faster and faster, eventually reaching a point where the repulsive force would overcome not just gravity, but all fundamental forces holding matter together. He called this scenario phantom energy, because the energy would have to violate standard assumptions about quantum fields. The equation of state parameter, a number called W that describes the relationship between energy density and pressure, would have to be less than -1. In standard physics, W can't be less than -1. It violates energy conditions. It implies that phantom energy creates its own energy as the universe expands, growing stronger even as space dilates. When Caldwell calculated the implications, he discovered something horrifying. If W is less than -1, even slightly, then the universe doesn't just expand forever. It experiences a runaway acceleration that ends in catastrophic disintegration. First, galaxy clusters would be torn apart, isolated galaxies flying away from each other faster than light speed. Then, individual galaxies would fragment as dark energy overwhelmed their gravitational binding. Solar systems would shred as planets were ripped from their stars. Eventually, Earth itself would explode as the expanding space between atoms became more powerful than the electromagnetic forces holding molecules together. The final stage would occur when even subatomic particles were torn apart. Quarks ripped from each other inside protons, electrons stripped from nuclei, the very quantum fields that define reality shredded by the accelerating expansion. Caldwell called it the Big Rip. The physics community largely dismissed the idea. Phantom energy seemed too exotic, too contrived. Most cosmologists assumed dark energy was simply Einstein's cosmological constant, constant by definition, leading to the gentler fate of heat death. But then astronomers began measuring dark energy's properties with increasing precision, and they found something troubling. Between 2005 and 2018, multiple independent surveys measured how dark energy's influence had changed over cosmic history. They used different techniques, analyzing supernovae, measuring the cosmic microwave background, mapping the large-scale distribution of galaxies, but they converged on a disturbing conclusion. The data was consistent with W being less than -1. Not conclusively. The error bars were large enough that W could still equal exactly -1, corresponding to a true cosmological constant. But the best fit value kept coming back slightly below -1. In 2018, the Dark Energy Survey collaboration published their results after analyzing over 200 million galaxies. Their measurement? W equals -1.00 plus or minus 0.05. The central value was exactly -1, but the uncertainty meant W could be as low as -1.05. If it really was -1.05, then the Big Rip was inevitable. The timeline depends on how far below -1 the true value lies. Caldwell's original calculations suggested that if W equals -1.5, the Big Rip would occur approximately 22 billion years from now. That might seem like an incomprehensibly long time, 50% longer than the current age of the universe. But cosmologically, it's just around the corner. More worrying, if W is time-dependent and getting more negative, if dark energy is actually accelerating its own acceleration, then the timeline could be much shorter. Some models suggest that if this is the case, the Big Rip could occur in as little as 16 billion years. That's only 2.5 times the current age of the universe. In cosmic terms, that's tomorrow afternoon. The scientific community remains skeptical. Extraordinary claims require extraordinary evidence, and measuring dark energy's equation of state with sufficient precision to distinguish between W equals -1.00 and W equals -1.05 requires incredibly sensitive instruments and meticulous analysis. But then, new evidence emerged from an unexpected source, not from distant supernovae or galaxy surveys, but from the quantum vacuum itself. The evidence forces us to confront an uncomfortable possibility. Reality might not be infinite. Reality might have an expiration date, and the countdown may have already begun.
Act 2. Accumulating evidence. The first hint that dark energy might be dynamical came from an entirely different field, quantum physics. In 2013, physicists at CERN's Large Hadron Collider detected subtle variations in the Higgs field, the quantum field that gives particles their mass. The variations were tiny, but they followed a specific pattern that suggested the Higgs field was interacting with something large-scale and cosmological. It was as if the quantum fields at the smallest scales were feeling the influence of something operating at the largest scales, explained Dr. John Ellis, a theoretical physicist at King's College London. The only thing operating at those scales is dark energy. The team published a provocative paper suggesting that dark energy might not be a separate entity from the quantum fields we study in particle physics, but rather an emergent property of those fields, specifically of how they interact as the universe expands. If that's true, then dark energy's strength should change as quantum fields evolve over cosmic time. The prediction was testable. If dark energy arises from quantum field interactions, then its strength should vary in regions of space with different quantum field configurations. In 2016, astronomers conducted an unusual experiment. They measured the expansion rate of the universe in different directions, looking for variations that would indicate dark energy wasn't perfectly uniform. What they found was startling. The expansion rate varied by approximately 9% depending on which direction they looked. The universe wasn't expanding uniformly. It was expanding faster in some directions than others. This phenomenon, called cosmic anisotropy, shouldn't exist if dark energy is truly a cosmological constant. Constants, by definition, are the same everywhere. But if dark energy is dynamical, if it's changing over time and varying across space, then anisotropy is exactly what we'd expect. More evidence came from studying the oldest light in the universe.
The cosmic microwave background, the afterglow of the Big Bang, contains imprints of conditions in the extremely early universe, just 380,000 years after time began. By analyzing subtle temperature variations in this radiation, cosmologists can reconstruct the evolution of cosmic expansion from the beginning until now. In 2019, the European Space Agency's Planck satellite released its final data set, the most precise measurement of the CMB ever achieved. When cosmologists analyzed this data to extract information about dark energy, they found something peculiar. The dark energy density inferred from the early universe was slightly different from the dark energy density measured today using supernovae and galaxy clustering. The discrepancy was small, only about 2 to 3 sigma, meaning it could be a statistical fluctuation, but it was in the exact direction you'd expect if dark energy was growing stronger over time. If dark energy was weaker in the past and stronger now, that would explain the tension between early universe and late universe measurements, noted Dr. Eleonora Di Valentino, a cosmologist at Durham University. But it would also mean we're not dealing with a cosmological constant, we're dealing with something that evolves. Perhaps the most compelling evidence comes from an observation that seems unrelated at first: the accelerating spin-down of pulsars. Pulsars are rotating neutron stars that emit beams of radiation like cosmic lighthouses. They spin with extraordinary regularity, more precise than atomic clocks in many cases. Astronomers use this regularity to test fundamental physics. As pulsars spin, they gradually slow down due to energy loss through radiation. The rate of slowdown is precisely calculated using general relativity. But in 2021, astronomers analyzing decades of pulsar timing data noticed something strange. Pulsars were slowing down slightly faster than predicted. The effect was tiny, only detectable because pulsar timing is so extraordinarily precise, but it was consistent across hundreds of pulsars scattered throughout the galaxy. What could cause this excess energy loss? One explanation, proposed by a team at the Max Planck Institute for Radio Astronomy, is that pulsars are losing energy to dark energy. Here's the mechanism. If dark energy is a dynamical field, something that can interact with matter and radiation, then rotating massive objects like pulsars would transfer energy to this field through gravitational coupling. The stronger dark energy becomes, the faster pulsars lose energy. It's like spinning a spoon in honey versus water. As dark energy density increases, it's like the honey getting thicker. Spinning objects feel more resistance. The team calculated how much excess slowdown you'd expect if dark energy has W slightly below -1 and is getting more negative over time. The predicted slowdown matched observations almost perfectly. This wasn't proof. There are other possible explanations for pulsar timing anomalies, but it was yet another piece of evidence suggesting dark energy isn't constant. Then came the observation that genuinely alarmed cosmologists. In August 2023, the Dark Energy Spectroscopic Instrument, DESI, released preliminary results from its survey of 6 million galaxies spanning 11 billion years of cosmic history. The survey aimed to measure dark energy's equation of state with unprecedented precision. The results showed something unexpected. W wasn't just possibly less than -1 in the present universe. It appeared to have crossed -1 only about 2 to 3 billion years ago. Before that, dark energy behaved like a cosmological constant with W equals -1. But recently, on cosmic timescales, something changed. Dark energy began getting stronger. The equation of state parameter began decreasing. If this trend continues, W will keep getting more negative. The acceleration will keep accelerating. The Big Rip won't just be a theoretical possibility, it will be inevitable. DESI emphasized caution in their announcement. The signal was only at 2.5 sigma significance, not strong enough to constitute a definitive detection. More data is needed. But cosmologists around the world immediately recognize the implications. If dark energy really is evolving, if it crossed from W equals -1 to W less than -1 just billions of years ago, then we're witnessing a phase transition in the fundamental structure of reality. Dark energy might not just be accelerating the universe's expansion, it might be preparing to tear everything apart. But this represents just one piece of a much larger puzzle hidden in the quantum structure of space-time itself.
Part B. Deeper implications. The most remarkable discovery involves the relationship between dark energy and the arrow of time itself. Time has a direction. We remember the past, but not the future. Eggs break, but don't spontaneously reassemble. Entropy, disorder, always increases. This directionality seems obvious to us, yet it's not explained by fundamental physics. The laws governing particles and forces work equally well forward or backward in time. There's nothing in the equations that says time must flow in one direction rather than the other. Yet flow it does. Why? The answer might be dark energy. In 2022, a team of physicists at Oxford University published a provocative paper connecting dark energy to the thermodynamic arrow of time. Their argument goes like this. Entropy increases because the universe is expanding. As space grows larger, there are more possible configurations for matter and energy, more ways for things to be arranged. Systems naturally evolve toward configurations that are more probable, and in an expanding universe, disorder is simply more probable than order. But here's the crucial insight. The rate at which entropy increases depends on the rate at which the universe expands. If expansion accelerates, entropy production accelerates too. And if dark energy is causing acceleration to accelerate, if we're headed toward a big rip, then the arrow of time itself is accelerating. Time is, in a very real sense, speeding up. Not in the sense that clocks tick faster, but in the sense that the universe is being driven toward its thermodynamic end state at an ever-increasing rate. The implications are profound and disturbing. We think of time as uniform. 1 second today is the same duration as 1 second yesterday or 1 second tomorrow. But if the thermodynamic arrow of time is accelerating, then the distance between now and the heat death of the universe is shrinking faster than time itself passes. It's as if we're on a treadmill that's constantly speeding up. We're running to stay in place, but the end is approaching faster than our running can compensate for. Sean Carroll, a theoretical physicist at Johns Hopkins University, has explored this idea extensively. If dark energy is phantom energy, Carroll explains, then we're not just headed toward equilibrium, we're being accelerated toward it. The universe isn't winding down gradually, it's being rushed toward its end state at increasing speed. But the evidence extends beyond thermodynamics into the realm of quantum mechanics itself. In quantum field theory, the vacuum, empty space, constantly fluctuates. Virtual particles pop in and out of existence, borrowing energy from the quantum foam for infinitesimally brief moments before annihilating. The rate of these quantum fluctuations depends on the structure of spacetime. In a static universe, fluctuations occur at a constant rate, but in an expanding universe, the expansion of space creates what physicists call a de Sitter horizon, a cosmic boundary beyond which events can never influence us because space is expanding faster than light can travel. The presence of this horizon changes the quantum vacuum's properties. It creates what's known as Hawking-Unruh radiation, a thermal bath of particles generated by the accelerating expansion itself. As the acceleration increases, the temperature of this radiation increases.
The quantum vacuum gets hotter in a thermodynamic sense. In 2024, physicists at the Institute for Advanced Study in Princeton calculated what would happen to quantum fields as dark energy approaches the Big Rip. What they found was chilling. As W drops below -1, the Hawking-Unruh temperature doesn't just increase gradually, it diverges, approaching infinity as you approach the Big Rip. In the final moments before reality tears apart, the quantum vacuum would become infinitely hot, not in the sense of particles moving rapidly, but in the sense of quantum uncertainty becoming infinitely large. The universe wouldn't just be torn apart physically, it would dissolve into quantum chaos, a state where the very concepts of space, time, and causality lose meaning. The Big Rip isn't just the end of structure, it's the end of definition itself. Reality would become fundamentally indefinite, neither existing nor not existing, but trapped in a quantum superposition from which nothing can emerge. Perhaps the most disturbing piece of evidence comes from studying the quantum entanglement structure of spacetime. Quantum entanglement, that spooky connection between distant particles that Einstein never accepted, isn't just a property of particles. Modern physics suggests that spacetime itself is woven from entanglement. The connections between quantum fields at different points in space create the geometry we perceive as distance and duration. If dark energy is tearing spacetime apart, it's not just pulling galaxies away from each other, it's literally ripping the quantum entanglement that defines spatial and temporal relationships. Researchers at the Perimeter Institute for Theoretical Physics have been studying how entanglement evolves in an expanding universe. In 2023, they published simulations showing that as W drops below -1, entanglement between distant regions of space begins to decay exponentially. Eventually, at the moment of the Big Rip, all entanglement across macroscopic distances would vanish simultaneously. Space would cease to be connected to itself. Time would lose its coherence. The universe wouldn't explode, it would simply cease to cohere. The universe wouldn't end with a bang or a whimper, but with a whisper of quantum confusion as the fabric holding existence together dissolved into mathematical abstraction.
Act 3. The Big Picture. The scientific theory that best explains all these observations is called quintessence, though the name belies its disturbing implications. Quintessence proposes that dark energy isn't a property of empty space, but rather a dynamical quantum field filling the universe. Like all quantum fields, it has potential energy and kinetic energy. As it evolves, rolling down its potential energy curve like a ball rolling down a hill, its properties change. If the field is rolling slowly, it behaves like a cosmological constant, with W approximately equal to -1. But if it starts rolling faster, if it begins accelerating down the potential curve, then W can drop below -1, entering the phantom energy regime. The question becomes, what determines how fast the field rolls? Several mechanisms have been proposed. One possibility is that quintessence is coupled to other quantum fields, the Higgs field, for instance, or the fields associated with neutrinos or dark matter. As these other fields evolve, they drag the quintessence field along with them, causing it to accelerate down its potential. Another possibility is that the potential energy curve itself is changing. Perhaps there's a higher level field, a field of fields that's modifying the landscape of quantum possibilities as the universe ages. If the landscape is tilting, the quintessence field would naturally begin rolling faster. A third, more radical possibility is that our universe is colliding with another universe in the multiverse. The collision would create stress in the quantum fields permeating both universes, potentially driving quintessence into the phantom regime.
Each mechanism makes different predictions about how W evolves over time and how other observable quantities should behave. Dr. Paul Steinhardt, director of the Princeton Center for Theoretical Science and one of the originators of quintessence theory, has spent decades exploring these possibilities. What's become clear, Steinhardt notes, is that if dark energy really is quintessence rather than a cosmological constant, then the universe's fate is not predetermined. It depends on the initial conditions of the field, on how it couples to other fields, on the shape of its potential curve. This introduces a profound uncertainty in cosmology. With a true cosmological constant, the future is calculable. Heat death in the infinite future. But with quintessence, the range of possible futures expands dramatically. In some scenarios, the quintessence field eventually reaches the bottom of its potential well and settles into a new cosmological constant with different properties than today's. The universe would continue expanding, but at a constant rate rather than an accelerating one. In other scenarios, the field never settles. It keeps rolling. W keeps decreasing, and eventually the big rip becomes inevitable. This forces us to reconsider fundamental assumptions about determinism and predictability in physics. We're accustomed to thinking that if we know the current state of a system perfectly, we can calculate its future evolution with arbitrary precision. This is the foundation of classical physics and remains largely true even in quantum mechanics, where we predict probability distributions rather than definite outcomes. But quintessence introduces a new kind of uncertainty, not quantum uncertainty arising from measurement, but cosmological uncertainty arising from our incomplete knowledge of initial conditions that were set 13.8 billion years ago. We can't directly measure the quintessence field's current velocity down its potential curve. We can only infer it from observations of cosmic expansion, and those observations have large enough uncertainties that multiple scenarios remain possible. We're like passengers on a train trying to determine whether we're accelerating or decelerating, explains Dr. Elena Aprile, a physicist at Columbia University. The metaphor is apt and terrifying.
Part B. Future Implications. Recent breakthroughs suggest we're on the verge of definitively determining whether the Big Rip is in our future. The Vera C. Rubin Observatory in Chile, named after the astronomer who discovered the first strong evidence for dark matter, began operations in 2024. Over the next decade, it will survey the entire visible sky every few nights, detecting billions of galaxies and thousands of supernovae. But more importantly, Rubin will measure how the dark energy equation of state has changed over cosmic history with unprecedented precision. By analyzing galaxies at many different distances and therefore many different epochs in cosmic time, astronomers will trace dark energy's evolution from billions of years ago to the present. If W is truly decreasing, if dark energy is getting stronger, Rubin will detect it at high statistical significance. We'll know within 5 years whether we're living in a Big Rip universe, states Dr. Željko Ivezić, director of Rubin Observatory. The data will be unambiguous. Meanwhile, gravitational wave astronomy offers an entirely independent way to probe dark energy's properties. The Laser Interferometer Space Antenna, LISA, will detect gravitational waves from merging supermassive black holes across cosmic distances. These mergers release precisely calculable amounts of energy in gravitational waves. By measuring how much energy reaches us, we can determine the exact distance to the merger. But gravitational waves also interact with dark energy as they propagate through space. If dark energy is dynamical, it affects how gravitational waves stretch and compress spacetime during their journey.
By comparing the gravitational wave distance measurements with electromagnetic distance measurements to the same events, LISA will determine dark energy's equation of state with extraordinary precision, potentially ruling out or confirming the phantom energy hypothesis within its first few years of operation. Gravitational waves give us a clean probe of spacetime, says Dr. Karsten Donsman, principal investigator for LISA. They're not affected by dust, gas, or any of the complications that plague electromagnetic observations. If dark energy is modifying space-time structure, gravitational waves will tell us. But perhaps the most ambitious proposal involves directly measuring the Hawking-Unruh temperature of the accelerating universe. This temperature is extraordinarily small, on the order of 10 to the negative 30 Kelvin, far too small to detect with any conceivable thermometer. But quantum systems can be extraordinarily sensitive to thermal environments. The proposal, called the Dark Energy Quantum Thermometer, would place highly entangled quantum systems in space and measure how quickly their entanglement decays due to interaction with the Hawking-Unruh radiation bath. If the Hawking-Unruh temperature is increasing, as it must be if W is less than -1, then entanglement will decay faster for experiments performed later in time compared to earlier experiments. We'll essentially be measuring whether the vacuum is getting hotter, explains Dr. Hongwei Hu, a quantum information theorist at Tsinghua University who proposed the experiment. If it is, that's a smoking gun for phantom energy. The technology to perform this experiment doesn't quite exist yet, but it's within reach. Quantum sensors have improved exponentially over the past decade, and several research groups are working on space-qualified systems that could fly within the next 10 to 15 years. What these future observations might reveal has profound implications, not just for cosmology, but for the future of intelligent life itself. If the Big Rip is confirmed, if we determine that W is decreasing and the universe really does have an expiration date, then every spacefaring civilization must eventually confront the same existential question: can we survive the disintegration of spacetime? Some physicists have explored potential survival strategies. One idea: construct quantum arcs, isolated pockets of space protected from the expanding universe by negative energy density. The Casimir effect, which generates negative energy between closely spaced conducting plates, might be scaled up to create bubbles of stable spacetime even as the surrounding universe tears apart. Another possibility: encode the information defining conscious minds into quantum states that could survive the transition through the Big Rip and reconstitute on the other side, assuming there is an other side where quantum states remain meaningful. A third, more speculative idea: advanced civilizations might learn to manipulate the quintessence field itself, locally altering dark energy's properties to stabilize their region of space. But all these scenarios require technology far beyond anything we currently possess or can even properly imagine. We're talking about manipulating the quantum vacuum, engineering space-time structure, controlling forces that operate on cosmological scales. If the Big Rip occurs in 22 billion years, humanity has time, barely. That's 15 times longer than we've existed as a species. Perhaps sufficient time to develop the technologies needed for survival. But if it occurs sooner, if W is dropping faster than current models predict, then we might not have enough time. And there's a darker possibility. Perhaps no amount of technological advancement can defeat the Big Rip. Perhaps, when space-time itself tears apart, everything built on that fabric must necessarily cease to exist. Perhaps the universe really does have a hard deadline, not negotiable, not defeatable, not escapable, just inevitable.
Act 4. The Ultimate Questions. The most profound implications emerge when we consider what the Big Rip tells us about the fundamental nature of time and existence. We typically think of time as a container, a stage on which events unfold, but something separate from those events. The stage persists even when nothing is happening on it. But general relativity tells us this is wrong. Time isn't separate from space and matter. Time is the evolution of geometric relationships between physical things. Without matter, without energy, without quantum fields changing and evolving, the concept of time becomes meaningless. If the Big Rip tears apart all structure, if it dissolves the quantum fields that define physical relationships, then it doesn't just destroy things that exist in time, it destroys time itself. This leads to a deeply strange conclusion. The Big Rip isn't an event that will happen in the future. It's an event that will happen at the end of the future. There's no after the Big Rip, no continuation of time once space-time coherence dissolves. The moment of maximum chaos, when W diverges to negative infinity and reality tears itself apart, is the last moment. Time doesn't continue past that point, not because everything is destroyed, but because continuing and past lose their definitions. The philosopher Ludwig Wittgenstein once wrote, "Death is not an event in life. We do not live to experience death." The Big Rip is the cosmological equivalent. It's not an event that occurs within the universe. It's the moment when the universe as a meaningful concept ceases. But perhaps the most mind-bending implication involves the question of whether the Big Rip has already occurred. This seems paradoxical. How could the universe have already ended when we're still here experiencing it? But quantum mechanics allows for possibilities that classical logic forbids. In quantum cosmology, the universe doesn't follow a single trajectory through time. It exists in a superposition of all possible histories simultaneously. Only when we make observations does one particular history become real relative to us. Some physicists have suggested that in the full quantum wave function of the cosmos, the Big Rip has already occurred in some branches, while remaining in our future in others. We find ourselves in a branch where it hasn't happened yet, not because we're special, but because only branches where it hasn't happened yet contain observers to ask the question. This is an application of the anthropic principle, the idea that we necessarily observe a universe compatible with our existence. But it leads to a disturbing corollary. If the universe's wave function includes branches where the Big Rip has occurred and branches where it hasn't, and if which branch we experience is genuinely probabilistic rather than predetermined, then every moment we continue to exist, every second that passes without reality tearing apart, represents an increasingly unlikely outcome. We're living on borrowed time in a probabilistic sense. Each moment we survive is a coin flip that happens to come up exist rather than cease. This isn't meant to inspire dread. The probability of the Big Rip occurring in the next second, or year, or even billion years is vanishingly small, but it does suggest that our continued existence is more contingent than we typically imagine. We're not just mortal individuals in an eternal universe. We're temporary patterns in a temporary cosmos, persisting only as long as the quantum odds favor our persistence. Yet there's a strange comfort buried in this terrifying realization. If time itself has an ending, if the universe really does have a finite temporal extent, then in some sense all of history happens at once. Past, present, and future become equally real, equally existent from a perspective outside of time. Your life, with all its moments of joy and suffering, exists as a permanent feature of the cosmic timeline, not perpetually in the sense of continuing forever, but eternally
in the sense of being timelessly embedded in the structure of reality. When we understand that time is finite, notes Dr. Lee Smolin, a theoretical physicist at the Perimeter Institute, we realize that nothing is truly lost. Every moment that ever occurs always occurs from the perspective of the timeless mathematical structure describing reality. The ending of time doesn't erase what came before, it completes it. This philosophical perspective, called eternalism or the block universe, suggests that death, whether of individuals or the cosmos itself, is less annihilating than we fear. Nothing ceases to exist, it simply ceases to be present.
What the evidence ultimately suggests about reality itself is this: we are participants in a finite story. The universe began at the Big Bang 13.8 billion years ago. The universe will end, possibly at the Big Rip, possibly 22 billion years from now. Between beginning and end lies the entire span of cosmic history. The formation of atoms, the ignition of stars, the emergence of galaxies, the evolution of life, the development of consciousness, the asking of questions like, why does anything exist at all? The story has a finite duration, but within that duration, infinite complexity unfolds, infinite meaning emerges, infinite beauty, infinite discovery, infinite possibility. Perhaps that's enough. Perhaps finite is more profound than infinite, because finite things are complete, while infinite things are merely ongoing. Perhaps the universe's approaching end, however distant, makes every moment more precious rather than less. Now, for concluding this journey. We began by asking what astronomers discovered when they measured distant supernovae in 1998. They discovered that time is running out, not in the sense of hours on a clock, but in the sense of the fundamental temporal extent of reality itself. The universe is accelerating toward a conclusion. Whether that conclusion is gentle heat death or catastrophic Big Rip remains uncertain, but that it's approaching, that time has a direction, and that direction has a destination, is now beyond doubt. Within the next decade, observations from Rubin Observatory and LISA will tell us which fate awaits. We'll know whether W is truly less than -1. We'll know whether dark energy is stable or evolving. We'll know whether the universe will end with a whimper or a rip. The current scientific consensus is that the evidence remains ambiguous. The best measurements suggest W is very close to -1, but the error bars are large enough that we can't definitively say whether it's slightly above or slightly below. Every new observation slightly narrows those error bars. Every year, our uncertainty decreases. Soon, within our lifetimes, we'll have the answer. But regardless of what that answer turns out to be, the Big Rip hypothesis has already transformed how we think about time, existence, and our place in the cosmos. It's reminded us that forever might not mean what we thought it meant, that the stage on which cosmic drama unfolds is itself dynamic, evolving, and ultimately finite. That everything we build, everything we discover, everything we become plays out against a clock that's counting down toward an inevitable conclusion. Yet this knowledge doesn't diminish meaning. If anything, it amplifies it. Every star that forms, knowing it will eventually die. Every galaxy that shines, knowing it will eventually be scattered into darkness. Every question we ask, knowing the universe won't last long enough to answer them all. Every moment of consciousness, every spark of awareness, every instance of something in the universe, understanding something about the universe, these become not less significant for being temporary, but more significant.
We are the universe's way of experiencing its own finite existence, of appreciating the brief window of time when structure and complexity are possible, of marveling at the improbable fact that matter can organize itself into configurations capable of wonder. The cosmic hourglass is indeed running. The sand continues its inevitable fall. But the universe is vast. The remaining time is still incomprehensibly long. The mysteries yet to be discovered remain endless. And we, brief patterns of organized complexity, aware of our own temporariness, yet choosing to explore and understand anyway, we continue the most audacious project ever undertaken, understanding the universe before the universe's time runs out. The clock is ticking, the questions multiply, the search for answers goes on.